To begin our study of modern electronic devices, we need to develop some of the theory behind semiconductor materials and their electronic properties. To do this, we need to start at the basis with material study, and that, of course, involves chemistry. All modern electronic devices, or I should say many modern electronic devices, are devices that are comprised of silicon materials, and silicon is a semiconductor material. So to understand how silicon behaves and how semiconductor materials behave, we're going to take a look at silicon. So on our periodic chart right here, silicon is an element that is in the third row and in column 14 here. So from this we can see that it's the 14th element, so it has an atomic number of 14, which means that it has 14 protons and approximately 14 neutrons. We're not going to worry too much about the neutrons. From chemistry we also know that we can represent the filling that if the silicon is a neutral atom, that it has to have a balance of protons and electrons. So, in addition to the 14 protons, if it's in charge neutral, it's going to have 14 electrons as well. You probably also recall from physics or from chemistry studying the rules for electron orbital filling. And this, of course, I've drawn a simplified model using Bohr's model. We, of course, recognize that the electrons are going to surround the nucleus of silicon, and they're going to be in these things called orbitals. The orbitals are not necessarily round. They have a different shape associated with them, but this is a good representation, a good model to work from. Now you probably remember having to memorize the orbital filling rules, the 1s2, 2s2, 2p6 stuff. So that stuff is going to come into play here because that corresponds to the energy that both the kinetic and the potential energy that these electrons have as they orbit the nucleus. Okay, so the 1s shell is lower energy, lower total energy electrons, and that's state is allowed to have 2 electrons in it, and the 2s shell, that s shell is allowed to have 2 electrons in it, and the p shell, 2p6, we're allowed to have 6 electrons. Okay, and we keep going on to fill our 14 electrons up. So we have to go to the 3s shell, and finally we get to the 3p shell, which has a slot for 6 electrons, but we only have 2 of those that are filled to make our total of 14 electrons. These 2 shells right here, the 3s2 and the 3p2 shell, are the shells that comprise the valence electrons. Those are the electrons that have the greatest amount of total energy associated with them. Okay, and from something in quantum mechanics called the Pauli exclusion principle, again, it's important to note that only 2 electrons can fill a particular or have the same energy level associated with them. So these shells right here, the 3p shell has 6 different energies that could be associated, or excuse me, 3 different energies that could be associated with the 6 electrons that are in that shell, and they all have a slightly different energy associated with them. Because silicon has 4 valence electrons, I should write 4 here, it's going to be able to bond covalently with other silicon atoms nearby. So we can kind of represent that in a 2-dimensional sense by saying each silicon atom here, each nucleus, is going to share with 4 of its nearest neighbors the 4 electrons, so that it has completely filled its valence shell. These are some of the rules that we've established from chemistry and are good predictors of how things will form together. And of course, it's important to note, and that you have probably or will cover this in materials, that this creates a crystalline structure, and this crystalline structure is actually three-dimensional. It's not flat. It has a crystalline structure associated with it based on how the molecules will arrange themselves. Now, how does all this stuff play into our understanding of semiconductor materials? Well, it's important to note that those energy shells and filling those energy levels is based upon a single atom model. All right, so if we look at silicon as a single atom, we can fill all of the valence shell, or excuse me, all of the energy levels. And what I have plotted here is a plot. On the y-axis is sort of arbitrary, but it's showing total electron energy. All right, so higher energy electrons are going to be higher up on the scale here. And in this direction, we're going to look at what happens when we go from a single atom, which has the band structure in a cartoon form, I guess, like this. And in particular, we're interested in these valence electrons right here in the 3 shell, the 3s and the 3p shell. Now, some interesting things happen when we go from a single atom model and we start combining. We bring more and more of these silicon atoms closer and closer to each other. That thing that I was talking about, the Pauli exclusion principle from quantum mechanics, tells us that we can only have 2 electrons that occupy the exact same energy level. So when we take a single atom and we bring it close to another atom, so if we have 2 atoms that are spaced nearer to each other, because of the Pauli exclusion principle and the rules of quantum mechanics, these shells right here, each atom is going to have a 3s shell, and because they can't have electrons can't fill those shells with the same energy, we're going to get a slight separation due to the proximity of silicon atom 1 near silicon atom 2, and there's going to be a slight shift in the 2 energy levels of those 2 atoms. Same thing happens with the p shell. All right, if we bring 3 atoms closer together, we're going to get these discrete energy levels, these individual energies that the electrons can have. But now, since we have 3 atoms close to each other, we're going to get more bands, or excuse me, more energy levels associated with the fact that we've brought these atoms closer and closer to each other. So as we start decreasing the atomic spacing, all right, so as we start going from single atoms that are distributed throughout space and start bringing them closer and closer to each other until we get to a silicon crystal, something interesting happens. What happens is the 3p energy levels all kind of combine and mush together, and the 3s levels combine and mush together, and they kind of expand the allowed energy levels. Well, then what happens is, because when we start bringing this atomic spacing closer and closer, we get some additional empty slots that some of the electrons in the p shell can fall down into this expanded s shell. And what eventually ends up happening is that when we get to the silicon lattice, the full lattice here, where we have a full silicon crystal, we have a range of values that are lower energy, which all of the electrons want to seek that lower energy, and we call that the filled valence band. So that's due to the expanding of this 3s level, or this 3s shell, and the allowed energies in there, and the 2 electrons that are in the p orbitals falling down into those expanded ranges. So now in a silicon lattice, instead of having these discrete allowed energies, we essentially have a continuum of allowed energies. We actually still have a bunch of discrete levels, but there's so many of them that we just pretend that this is a continuum of energy levels that are allowed for these valence electrons. And then the p shells up here, because they're expanding and because we're getting more orbitals closer to each other, we have this empty conduction band, this thing called the conduction band, where we have these empty states where electrons could reside, but because this is a higher energy state, they're going to want to reside in this lower energy state, which we call the valence band. And in semiconductor materials like silicon, this expansion of the allowed energy levels due to bringing the atoms closer together, also results in this thing called a band gap. And this band gap is an area of disallowed states. All right, and from the just the way that the mechanics work here, the quantum mechanics work, is that we basically have this these energy levels right here that an electron cannot possibly occupy within a silicon crystal. So we can have electrons in this valence band, and also these bands are going to expand further down here, but we tend not to worry about the bands that are closer to the nucleus, because what we're going to be interested in is how easily higher energy electrons can become excited and move throughout the crystal. So in this state, once we're in the silicon crystal, we're primarily concerned with these valence electrons, and most of the valence electrons are going to be located in this valence band. But if we provide sufficient amount of energy, either through thermal energy, through electrical energy, or in some cases light, we will give an electron that is in this valence band right here sufficient energy to promote itself, or to jump up into this thing called the conduction band. And when that electron is excited somehow, gains that energy, when it's in the conduction band, it becomes free to sort of wander throughout the crystal. So again, in this model right here, where we have all of these electrons represented by dots, they're tightly bound to the nucleus. But if enough energy is given to one of these electrons so that it will populate this conduction band, what can happen is that this electron then is free to kind of wander throughout the crystalline structure. So if this electron right here, for instance, is given enough energy to promote itself to the conduction band, what it can do is it can kind of wander over through the crystal. And what this allows, and this is the reason these are called semiconductors, is that if sufficient energy is provided to that semiconductor so that electrons can be promoted from the valence band up into the conduction band, then we have a mechanism through which we can support current through the silicon crystal.